So the question is, what is performance? Okay, so probably have seen this before in other courses. So really, we would like to make here some intelligent choices about computers. Okay, so we ask, for example, why some computer hardware performs better at some programs but performs less at other programs. So how do we measure the performance of a computer system? What factors are related to the hardware? What factors are related to the software? We need to have like a good understanding of this topic. And how does the machine instruction set affect the performance? For example, instruction sets are designed to improve the performance. So this is understanding the performance as a key to understanding the underlying organizational motivation. So this is our topic in this presentation. Okay, so this might take more than one lecture to cover this topic. Okay, so the first thing I need to talk about is the difference between response time and throughput. So these are two ways to measure the performance. The meaning of response time, it's the time between the start and the completion of a task as observed by the end user. That's the meaning of the response time. So this is the CPU execution time plus the waiting time. So when you look here at the task, okay, you can look at the time when the task started, you can look at the time when the task completed. So the time in between is what we call the response time. Of course, the less response time, the better. Yani it will be the shorter the time, the better, the higher is the performance. So part of the response time is the time that the program spends executing on the CPU. So this is called the CPU execution time. And part of this is the waiting time. Yani, for example, the program might be waiting for input. It might be waiting for output or for the operating system to schedule the program to execute on a CPU. For example, all the CPUs might be busy and therefore the program might be waiting. So this is called waiting time. Okay. On the other hand, we have throughput. Throughput means that the number of tasks, here task means a program. So the number of tasks the machine, the computer can run in a given period of time. And if you can execute the same program, okay, let us say 10 times in each, let us say, second or in each minute, then this is actually called throughput. Okay, so the number of tasks, okay, in a given period of time. Now, if we decrease the execution time, we can improve the throughput. For example, if you use a faster version of a processor, we can have less time to run a task. Therefore, we can run more tasks, okay, in a given period of time. Increasing the throughput can also improve the response time. So these are related. So for example, if we use a multiprocessor and we have a large number of processors and you have more tasks, okay, we can actually execute them in parallel. So these tasks can be executed in parallel on different processors. And because they are running in parallel, we can increase the throughput. And we can also decrease the waiting time. Why? Because there is no queuing here. We are not really scheduling all of these tasks to run on the same processor. So therefore, they can run in parallel. And by running them in parallel, we can reduce the waiting time. And by reducing the waiting time, we can reduce the response time. Okay, is this clear?
Yes.
So you can see that response time and throughput are related. Okay, so remember that response time is just time, and you can measure it in seconds, in minutes, in hours. That's response time. And throughput means that how many tasks you can execute in a given period of time. Okay. For example, if you are using a server, okay, so if you have a server, you would like to execute more tasks, okay, in a given period of time. You might actually have hundreds, thousands, or even millions of users. For example, if you are using something like Google, and Google is going to receive requests, okay, all over the internet from millions of users. So the more requests, okay, it can execute, okay, in each second, then this will be the higher will be the performance. So here the meaning of throughput, okay, is related to the number of tasks that a given machine can run in a given period of time. Okay. And in order to handle this large number of tasks in a given period of time, you have to use a multiprocessor, a large number of processors. Fine. Otherwise, the waiting time is going to increase a lot, and therefore this is going to reduce the response time. So by having a long waiting time, then this is going to increase the response time of a given task. So now, okay, how is the textbook defines performance? It's based on execution time. Really, it's really based on execution time. So the less the execution time, the higher is the performance. As simple as that. So if you can reduce the execution time, you can increase the performance. So we can say that given a machine X, here a machine, I mean a computer system. So we can say the performance of X is inversely proportional to the execution time. So it's defined as 1 over the execution time. So all what we care about is the execution time, and we would like to reduce the execution time. By reducing the execution time, you can improve it. Now, you can relate two computer systems, X and Y. You can take the same tasks, okay, the same, let us say, the same application, the same program, and you can run it on two different computers, X and Y. Now, we can say that X is n times faster. So how do we compare the performance of two computer systems, X and Y? We use division, okay? So that's really the idea. So what we do is that we divide the execution time on Y divided by the execution time on X. So we say that X has higher performance, or n times faster than Y. Okay, by looking at the execution, we divide the execution time on Y divided by the execution time on X. So if this ratio is equal to n, it means that the execution time on X is n times shorter than Y, or the execution time on Y is n times longer. So the ratio of the execution time divided by the execution time is equal to n. But notice that we are dividing the execution time on Y divided by the execution time on X. If this ratio is equal to n, and this n is greater than 1, so we say that X is faster than Y by this factor n, by this ratio. Yani, for example, if we get n is equal to 2, we say that computer X is 2 times faster than computer Y. And in other words, if you take the same application, the same program, and you run it on computer X and computer Y, then you should really get the execution time on X is half the execution time on Y. So the ratio will be equal to 2. Or in other words, the execution time on Y will be twice, okay, the execution time on X. So the ratio, when you divide the execution time on Y divided by the execution time on X, you get 2. Clear? Is this clear? It's a very simple definition. Yes. Okay. So now what do we mean exactly by execution time? We can look at the real elapsed time. That's actually how many, let us say, people, when they would like to look at the computer system, they would like to look at it from the outside. So they don't really care what's really going inside. You just look at real time. That's it. So you count everything. You count the waiting time, you count the time for input and output, you count the disk access time, you count the operating system scheduling time. So all of this is time, and all of this is part of the real elapsed time. Okay, and many people just use just the real elapsed time. That's it. Now this is very useful, but it's not really good if you would like to compare two different CPUs. So for this reason, we're going to focus here on the CPU execution time. So we'll not take into account the waiting time or the input output, because this is really related to I/O. and it's not related to the CPU. If I would like to compare two different CPUs, I really would like to focus on the CPU execution time. Okay, so it's not related to the operating system scheduling because this is actually just the OS itself. So we focus on the CPU execution time. So here we look at the time while the CPU is executing the program instructions. That's the time the program is spending running on the CPU. So again, we're not going to count here the waiting time for input and output. If the program is reading, let us say, a file from the disk, okay, so it's waiting, so this is waiting time. So we're not going to count this because this is related to the how fast is the disk access, okay? How long does it take to access, okay, the file and to read the file from the disk? We're not going to relate this to the operating system scheduling, okay? Again, this is not really, so we assume that the program is running on the CPU and would like to count the CPU execution time. Now, this can be measured in just as time. We can measure it in seconds or in milliseconds or in nanoseconds, depending on, of course, how long or how fast the program actually runs. So it is just measured as time, okay? So we just use the unit of time, which is seconds, or we can use, okay, the other units like milli and micro and nanoseconds. Or we can relate it to the number of CPU clock cycles. Now, there is a clock inside the CPU. And this clock, you can actually, rather than measuring it, the CPU execution time, rather than measuring it as time in seconds, you can relate it to the number of clock cycles. So you just count the number of clock cycles because clock cycles here means time. So we can relate the CPU execution time to the number of CPU clock cycles. So let us take a look at this equation. Okay, very simple math. So we look here at the CPU execution time. Okay, that's the CPU execution time. We can count the number of CPU cycles. So we look at the program. The program is running inside the CPU, and it's going to take, these instructions are going to take a certain number of clock cycles inside the CPU and multiplied by the cycle time. Okay, so we multiplied by the cycle time. Now the cycle time, what's the cycle time? Is just 1 over the clock rate. So we can also, knowing the clock rate or the clock frequency, we can divide the number of CPU cycles by the clock rate or the clock frequency. Okay, so that's here the meaning of the clock rate. It is just the clock frequency. All right, so and is this clear? Do you have any question about this?
It's clear, Doctor.
Right. So let us take a look here at the clock cycle. So what is the clock cycle? Now, the clock itself is something which is very important signal which exists in digital hardware. So today, if you look at the CPU is nothing but a sequential circuit because it has registers and it has memory elements. So there is a clock. Okay. So we have seen the clock when I talked about the single cycle CPU design. So the clock is very important. Why? Because it is used to synchronize the operation of the digital hardware. And remember that CPUs are nothing but sequential circuits. So therefore, they have to be synchronized. And for this reason, we need a clock. And the clock is a periodic signal. So there is a clock cycle. And this clock cycle is a time duration. You can see that this is the clock cycle. It's the time duration between two rising edges of the clock. So between one rising edge and the next rising edge. That's the duration of one clock cycle. Part of this clock is a high level and part of it is a low level. And the same clock cycle repeats over and over again until, of course, you power down, you turn off, okay, your computer system or your processor. So if you shut down the clock, then khalas, it will turn, if you turn it off, the processor, then the clock will stop. So the clock is always ticking. Okay, and it has exactly the same. So the same clock cycle is repeated again and again. Now, during one clock cycle, you can do a computation, or you can do a data transfer. And you can transfer, let us say, data from memory into the CPU, or you can be doing a computation inside the CPU. And then at the edge of the clock, notice that this is at the edge of the clock, we update the state. Yani we update, let us say, a register, one or more registers inside the CPU. We have seen that in the case of the single cycle CPU, we update the program counter, okay, at the edge of the clock. So we increment the program counter so that we point to the next instruction memory. We write the result to a register in the register file. So we update a register. Sometimes we write to memory. So we update the state. So the meaning here of state is that whatever you are storing inside the registers or the memory elements, okay, then this is the state. Okay, so we update it at the edge of the clock. So the definition of the clock cycle, it is just a clock period, and it is a duration, a time duration between two consecutive rising edges of the clock. Now, remember that the clock cycle is nothing but time, and it is measured in seconds or milliseconds or micro or nano or even picoseconds, okay? Depending, of course, on how short this clock cycle. Now, the shorter the clock cycle, the higher is the clock frequency. So we call it clock rate or clock frequency, and it is simply equal to 1 over the clock cycle. That's the definition of the clock frequency. So it's sufficient to know the clock cycle to calculate the clock frequency, or vice versa. And if we know the clock frequency, we can calculate the clock cycle. If we know the clock cycle, we can calculate the clock frequency. So you don't need both. You just need one number to calculate the other. Now, the unit of the clock rate or the clock frequency is the hertz. So when I say 1 hertz, it means 1 cycle per second. So this means that the duration of one clock cycle is 1 second, and therefore you have in each second you have 1 cycle. 1 kilohertz, on the other hand, the K here means 1,000. So 1,000 cycles per second. So in each second, the clock is going to repeat 1,000 times. So we say it 1,000 hertz or 1 kilohertz. And it means that you have 1,000 cycles in each second. Now, if you have 1,000 cycles per second, then the duration of one cycle will be what? What will be the duration of one clock cycle? If you have 1 kilohertz?
1 millisecond.
1 millisecond, yes, thank you very much. So you have to reduce the cycle to 1 millisecond so that you have 1,000 cycles in each second. Like 1 megahertz means 1 million cycles per second. That's the meaning of 1 mega, 1 million cycles per second. And therefore, if you have 1 megahertz, what should be the duration of one cycle?
1 microsecond.
Yes, 1 microsecond. And if you have 1 gigahertz, if you have the clock frequency is 1 gigahertz, then you have 1 billion, okay, cycles per second. What will be the duration of one cycle?
1 nanosecond.
Yes, 1 nanosecond. So you see that actually how they are related, okay? So 1 nano, you have to reduce the clock cycle to 1 nanosecond, okay, to have a 1 gigahertz clock frequency. So for example, if you go and buy a computer system that has a 2 gigahertz clock, if you go, for example, buy a laptop, for example, okay, that has a 2 gigahertz clock frequency, then you say, what's the cycle time? It will be 1 over 2 billion hertz. So here it will be 1 over 2 will be 0.5. 1 over 10 to the power 9 is 10 to the power negative 9 seconds. So this will give you nanoseconds. So therefore, if you have 2 gigahertz, then the clock frequency is even less than a nanosecond. It's half nanoseconds or 0.5 nanoseconds. So this is the clock cycle okay, when the clock frequency is 2 gigahertz. So the higher the clock frequency, the shorter is the clock cycle. Okay, clear? Very clear?
Yes, clear.
Yes.
Right. So you see
Doctor,
that, yeah.
I have a question. Why in some, for example, in my laptop, it says 2.4 gigahertz, but when I see the actual speed, it says it's higher. For example, 2.9 gigahertz or something.
So you see that today CPUs are very sophisticated. They can change the clock frequency dynamically at runtime. So for example, if the CPU is very busy executing too many instructions, sometimes the CPU will increase the clock frequency. So it's actually capable of running at higher clock frequencies. So it's going to increase the clock, okay, so that it will run the program faster by increasing the clock frequency. You will see that, okay, by increasing the clock frequency, we can reduce the execution time. And therefore, it will be actually, this is what the CPU does. So it will, if the CPU is running let us say many instructions, and it would like to speed up the execution of the program, it would like to reduce the execution time, then it will increase dynamically. This is not automatically by the hardware. It's going to increase dynamically the clock frequency. Now, there is one problem with increasing the clock frequency. The CPU will start consuming more energy per second. So therefore, it's going to increase the power consumption. And by increasing the power consumption, it's going to start heating. And therefore, it's going to increase its temperature. And therefore, the CPU, at some point, it cannot increase too much the clock frequency because the power consumption will be so high, a lot of heat will come out of the CPU, and this might damage the CPU. So for this reason, I'm going to start to lower down, okay, the clock frequency to cool it down, okay? I'm just mentioning here something. Do you understand this?
Yes.
Okay, so you see that today, actually, CPUs are very sophisticated. They can change the clock frequency. They can increase the clock frequency to speed up the execution of a given program and reduce the execution time, okay? But this is going to heat the CPU because the higher the frequency is higher the power consumption. And the higher the power consumption, if it's going to consume, okay, higher power, then it's going to heat up all of these transistors. And these are going, we have billions of these on a single chip. And therefore, these are going to start producing more heat. And at some point, the CPU cannot really run at very high temperatures. Okay, otherwise, it's going to break down, it's going to melt. Okay, so for this reason, they lower, okay, the clock frequency to cool it down, okay, to an acceptable temperature range. So that's why we cannot actually go, for example, to terahertz. Okay, so if you have like 1 terahertz, you have 1 trillion cycles per second, and therefore the clock cycle will be in picosecond. So 1 terahertz means that the clock cycle is picosecond. So for this reason, you don't really find computer systems that run at such high frequencies because the amount of power consumed will be so high, and the amount and the temperature, the cooling becomes so expensive. You cannot really cool it with air, with a fan. You have to use some kind of liquid cooling. And even that will not be sufficient, actually, if you are using terahertz. So 5 gigahertz maybe today is the limit, okay, for the highest and the fastest CPUs. All right, so so I mentioned here the clock cycle and the clock frequency. Let us move on. Now, in the past, back in the 1970s, people did not really use very high clock speeds. It used to be like around less than a megahertz. Okay, back in the 1970s, 1980s, it became like tens of megahertz, and then it increased to hundreds of megahertz in the 1990s until it reached the gigahertz. Okay, so why? Because at that time the transistors were slow, switching them on or off was slow. So therefore, the circuits, okay, the gates had higher delays, and because of the delays that exist inside the gates and inside the circuits, This is actually means that you have to use a slow clock. Okay, that is not related to the power consumption. This is related to the delays that exist inside the gates and inside the circuit. But today the gates are a lot faster, okay, than decades ago. So they can actually be switched on and off very quickly, very fast. So you can easily use gigahertz. So the clock frequency has improved by a factor by more than 1000x, okay? Maybe 10,000x or 100,000x if you go 2 decades ago. So how do we improve the performance? Now, we can reduce the number of clock cycles. So to improve the performance, we have to decrease the execution time. As we have seen here in the previous slide, the CPU execution time is related to the clock rate. So if you increase the clock rate, you decrease the clock cycle and you reduce the CPU execution time. As simple as that. Or you need to reduce the number of CPU cycles. So that's how we improve the performance. So either reduce the number of clock cycles which are required by a given program. If we reduce the number of clock cycles, the total number of clock cycles, you can reduce the execution time. Or you can reduce the clock cycle time. That will be a second option because these two things appear. So either reduce the number of clock cycles or reduce the clock cycle time. If you reduce the clock cycle time, it means that you have to increase the clock cycle. Here's an example. Suppose that we have a program that runs in 10 seconds on a computer X that has a 2 gigahertz clock. So 10 seconds on a computer that has a 2 gigahertz clock frequency. Now, the question is, what's the number of CPU cycles on computer X? How do you solve this? Quick answer. How do you solve this? So shall I mention you by name? You actually would like to volunteer? Yes, تفضل.
Yes, Doctor.
Yes, Khalid.
We have 2 gigahertz means we have 2 to the power 2 times 10 to the power 6 cycles per second.
No, 9. Giga means
sorry, 9 cycles
yes.
per second.
Yes.
And we have 10 seconds. So we divide 10 to the power 9. 2 times 10 to the power 9 divided by 9, we get the number of cycles. Right.
Sorry, I did not understand. You do what? So the clock frequency is 2 gigahertz. It's yes, 2 times 10 to the power 9 cycles per second. What I need is I need the number of CPU cycles. So how do you calculate the number of CPU cycles?
Just simply
what do we do?
Multiplying 10 seconds by 2 gigahertz.
Yes. Now look at the units. Just look at the units. So to calculate the number of cycles, I need to multiply. This is actually the answer I wanted from you. I want to multiply 10 seconds by 2 gigahertz because 2 gigahertz means 2 billion cycles per second. So in 10 seconds, how many billions of cycles? That's the question. So multiply 10 seconds by 2 billion cycles per second, you get 20 billion cycles. So in 10 seconds, there are 20 billion cycles. That's the number of CPU cycles in 10 seconds if the clock frequency is 2 gigahertz. Is this clear?
Yes.
Is this clear, Khalid?
So much.
Yeah, it's very simple.
Yes, Doctor.
Yeah, so that's actually is the answer that I was looking for. Right. So now we want to design computer Y, okay, to run the same program in 6 seconds. The question is why? No, before the question, now there is something here that Y requires 10% more cycles to execute the same program. So you take the program from computer X and you would like to run it on computer Y, but the number of cycles is going to increase on computer Y. So rather than taking, let us say here, 20 billion cycles, is going to take 10% more cycles to execute on computer Y. Now you say that why 10% more? Well, it depends on the implementation of these instructions. Some instructions might take more cycles to execute. That's it. So 10% more cycles The question is, what is the clock rate for computer Y? This is the question. What's the clock rate for computer Y? Now, first, let me ask you this question. What's the meaning of 10% more cycles? What do you understand from this?
That's mean computer Y is multiple. I mean, the n of the computer Y is 1.1. So if we can say 100% for the Y, it is 10% more, which is 110%, which is 1.1. We multiply
Yes, thank you, Ali.
1.1.
Thank you. Yes. Do you understand what Ali is saying? For the rest of the students who are sleeping,
Yes.
wake up.
Performance
Okay.
between X and Y.
Yeah, so I really actually, even when we have face-to-face lectures, I see also sometimes sleeping faces. Okay, so even though the camera is turned off, I can see that you are sleeping. Okay, I can see that. Anyways, let us focus here. So when we say 10% more cycles, okay, more. So we have to add the 10% to the 100%. So this will give me 110%. So therefore, all what we have to do is multiply these 20 billion cycles by 1.1. That's it. Because if you multiply it by 10%, which is 0.1, so 10% is nothing but the number 0.1. Okay, that's the meaning of 10%, 0.1. And then you added to the number of the 20 billion cycles. So you take 20 billion cycles and then you add to it 10% of 20 billion. So this will be 20 billion times 0.1, which are just 2 billion. It's the same thing as multiplying the 20 billion cycles by 1.1. So that's just how I read the English language, and I convert it into a mathematical equation. That's it. Okay? Very simple math. It's not really that difficult to understand. So all what you have to do, in order to calculate the number of CPU cycles on computer Y, so I need to calculate the number of CPU cycles on computer Y. So we take the CPU cycles on computer X and we multiply it by 1.1. So if you do this, you get 22 billion cycles. That's the number of CPU cycles that I need to execute on computer Y. Fadal Abdurrahman.
So what is the frequency for computer Y? How to get
Well, we did not calculate it yet. I just calculated the number of CPU cycles. Now you tell me, Abdurrahman, what will be the clock frequency for computer Y?
I will need to divide by 6.
Yes. Now, in order to calculate the clock frequency on computer Y, we need to execute 22 billion cycles in 6 seconds. Because it says that we want to design a computer Y to run the same program, but now the same program has 22 billion cycles. But I would like to execute these 22 billion cycles in 6 seconds. So to calculate the clock frequency, simply divide the 22 billion cycles by the 6 seconds. Now this will give me the clock frequency for computer Y. If you divide 22 billion by 6, you get 3.666. So we can round it to 3.67. And this will be times billions of cycles per second. So this will be 3.67 gigahertz. Okay. Any question about this? Fine. So now there is an important metric, okay, which is used in CPUs, which is called the clock cycles per instruction. Now, in a real CPU system, on a real processor, instructions can have different number of clock cycles to execute. Now, in the case of the single cycle CPU, we assume that each instruction will take 1 cycle, but that's not realistic. Okay, it was not realistic because sometimes you have simple instructions, sometimes you have complex instructions. Yani, for example, if you have a multiply instruction, definitely multiplication is going to take longer than addition, because in order to multiply, let us say 2 32-bit numbers, is going to take longer. Okay, it's going to take longer to execute. So therefore, the number of clock cycles per instruction, so I call it clock cycles per instruction, or CPI. Cycles per instruction, that's the CPI. It's a very important metric. Now that can change from one instruction to another instruction. Yani, for example, if you have a floating point instruction, a floating point addition, this will take longer than an integer addition. Okay, integer addition is simple. Floating point addition is not simple. Why? Because we have to look if the exponents are different. We have to take the exponent difference. We have to shift the significant to align them, and then we have to add, we have to normalize, we have to round. You see, it takes longer, okay, to execute a floating point addition. Accessing memory will take longer than accessing the registers. So for this reason, instructions have different CPIs. So the question is, what is the average CPI for a given program? So we need to define here the CPI as an average number. If you have a program, and this program consists of multiple instructions, of course, the program will execute probably billions of these instructions. But, okay, we need to calculate here, and each instruction can have a different number of clock cycles. What's important for us is the average CPI. Here's an example. Suppose that the first instruction, instruction 1, will take only 1 cycle. The next 4 cycles will be for instruction 2. So instruction 2 takes longer to execute. Then instruction 3 will take 2 cycles. Then instruction 4 will take 1 cycle, and so on. 5 will take 1 cycle. 6 will take 2 cycles. 7 will take, instruction 7 will take 3 cycles. Right. So what is the average? What is the average CPI if we only have 7 instructions in the program in this example? How do you calculate the average CPI? You tell me.
We count the number of instructions and divide it by 7. Yes.
So we count what?
Number of cycles.
Yeah, we count the number of cycles. It says that we have 14 cycles
over the number of instructions.
So we need actually to divide the number of cycles divided by the number of instructions, because it's cycles per instruction, right? So how many instructions do we have in this program?
7.
So these 7 took 14 cycles. So divide 14 by 7, you get 2.0. Now this is an average number. It does not really have to be an integer. You might get 2.1, 2.2. That's fine. Okay. So that's the average CPI. For this example, it turns out to be 2.0. Okay, is this clear? That's what we call the average CPI. All right. Now, this is something which is important now, is that if you change the cycle time, if you increase the clock frequency, sometimes the instructions will start taking longer, more cycles to execute. And if you use, let us say, a shorter clock cycle, that might also impact the number of cycles per instruction. So this is something which is also important, and designers have to take this into account. If you would like to use a higher clock frequency, then this means that, well, the instruction might take longer to execute, more clock cycles to execute. So now we come to the performance equation. If I would like to execute a given program, so the program consists of a certain number of instructions, machine instructions. Remember that the CPU is only executing these machine instructions. And these machine instructions are going to take a certain number of clock cycles. And the cycles, each cycle has a duration, time duration, according to the clock cycle. Okay, so, or the clock periods defined in nanoseconds. So you multiply the number of clock cycles by the cycle time. This will give you the number of seconds which are needed to execute a given program. Now, if you would like to relate, remember that I talked in the previous slide about the average CPI. Okay, so the average CPI, I'm going to use, just give me 1 second. So this is my pen tool. So if I would like to write here an equation for the average CPI, how do I write it? I say that the CPI, the average CPI, is equal to what?
A number of cycles over the number of instructions.
So the total number of cycles divided by the total number of instructions. You agree?
Yes.
Yes.
That actually is my average CPI. Now, from the same equation, I can say that the CPU cycles, to calculate the CPU cycles, if we know the average CPI, multiply it here by the, if you multiply it by the total number of instructions. So if you count the number of instructions and we know the average CPI, you can also calculate the CPU cycles. Correct? From the same equation. So knowing the average CPI, knowing the instruction count, I can calculate the total number of CPU cycles. Correct?
Yes, correct.
Okay, it's just the same equation. I'm just rewriting it differently. Fine. Now the CPU execution time. What's the CPU execution time? Well, we look at the total number of CPU cycles. These are the CPU cycles. And we multiply it by the cycle time. But the CPU cycles is the instruction count multiplied by the average CPI. And then we multiply it by the cycle time. Correct?
Yes, correct.
So this is known here as the performance equation. Instruction count multiplied by the average CPI multiplied by the clock cycle. This is the CPU execution time. So this is known as the performance equation. Okay. Notice that in the performance equation, I have three factors. I have instruction count, I have the average CPI, and I have the clock cycle. Let us understand this equation. So we have these three factors. Okay. Now, inside the computer system, we have a program. The program is written in a high-level programming language. There is a compiler that's going to translate the program from high-level programming language into low-level, and of course into assembly, and then from assembly into machine instructions. There is the instruction set architecture. So this is the program. This is the compiler. We have the ISA. We have this. This is the instruction set architecture that defines the instructions that are implemented by the CPU and the hardware. We have the organization, which means that how these instructions are implemented, okay, by the CPU. And finally, we have the technology, the transistors, okay, how fast these transistors, okay, can switch on or off. This is the technology that we have, okay? Right. So if you look at the instruction count, the first factor, the instruction count is related to the program. Agree? So I'm putting a check here, and X, it means that it is related to the program, how the program is written. Now, remember the courses that you have taken about algorithms and data structures and so on? Remember these courses? They talk about the big O notation, right?
Yes.
Why do they talk about the big O notation? They will tell you this is big O of n, or this is big O of n squared, and so on. What does it mean?
Time performance.
The worst case?
Well, they are counting the instructions. They are counting the instructions, but they don't tell you this. I'm telling you it. Okay. So basically, when you write an efficient algorithm, you can reduce the instruction count because the program is written in high level and the compiler is going to translate it to low level. So if you write actually an algorithm which is more efficient, so this is pure software. This is pure software. It has nothing to do with the hardware. If you write a better program, you use better algorithms, you can reduce the instruction count. Remember, for example, bubble sort and quick sort. We know that quick sort is faster than bubble sort or insertion sort. Have you studied these?
Yes.
Yes.
Okay, what is the difference between these? It's the instruction count. It is the instruction count. So the program can execute with less instructions and it will do the same thing, it will sort. But it sorts with less instructions. So this is the meaning of the instruction count. So the instruction count is related to how the program is written in a high-level programming language. If you use actually fast algorithms or use actually slow algorithms, so your program can be really very slow or fast, depending on the algorithms that you have written. So that's actually is the instruction count. It also depends on the compiler, because the compiler is going to do the translation, okay, from high level to low level. Some compilers are really generate bad code, okay, or slow code. Some compilers actually can generate very efficient code. So the way that the program was translated by the compiler also, it will impact the instruction count. Okay? And finally, it's related to the instruction set architecture. Okay, what are the instructions that exist in the architecture? Sometimes there are better instructions in the architecture, and therefore you can reduce the instruction count. The instruction count is not related to the organization. It's not related to the technology. It has nothing to do with it. Okay? So notice that there is no X for organization and for technology. It is just left blank. Right. How about the average CPI? Now, the average CPI is not related to the algorithm. It's related to the compiler. It's related to the ISA, and it's related to the organization. Now, in the case of organization, it's very easy to understand. Why? Because, for example, if you have a multiplier in the hardware, now multiplication can be, you can actually have very fast multiplier that might take 2 or 3 cycles to do one multiplication, or you might actually have a very slow multiplier that might take, for example, let's say 30 cycles, okay, to do one multiplication. So the number of cycles per instruction is going to increase if the organization is bad, okay? The number of cycles per instruction is going to increase. It will also depend on the ISA and the compiler. Now, the compiler here might not be really clear why it depends on the compiler, because it depends, of course, how the compiler has translated the program. Yani, for example, if you have, let us say, a variable multiplied by 2, if you have x multiplied by 2, now you can use the multiply instruction to multiply by 2, or you can use shift left to multiply by 2. So if you shift left the bits by 1 bit, and this is an integer, you can multiply by 2, right? But shift left can run much faster, okay, in the CPU than the multiply instruction, and therefore you can reduce the CPI by having a better compiler that can use, if you have more than one translation, okay, for the same expression. If the compiler can do a better job in the translation, it can reduce the average CPI. And of course, it depends on the instruction set architecture. These are the instructions that exist in the CPU. Finally, the clock cycle, the last one, depends on the organization and the technology. If you improve the organization, this is why I'll talk about pipeline CPU, you can reduce the clock cycle. Of course, you can also improve the clock cycle by using actually faster transistors which are related to technology. That is also obvious, okay? And you can improve the clock cycle, you can reduce the clock cycle by improving the technology. So you can see that part of this performance equation, which is the execution time, part of it is related to the software and part of it is related to the hardware. So both are needed to improve, to reduce the execution time of a given program. So this is the picture that I want you actually to understand about the performance equation. So suppose we have 2 implementations of the same instruction set architecture. What does this mean? 2 implementations of the same ISA. Can we have 2 implementations of the same ISA?
I mean, same interface, as we said.
No, the same instruction set architecture. Okay, so how can we have 2 implementations of the same instruction set architecture? Can you tell me how?
It's the same CPI, it will be?
No. What does it mean, this statement, to have 2 implementations of the same instruction architecture? So we're not really changing the instruction set architecture, we're changing the implementation. So how can we have 2 implementations of the same instruction set architecture?
Like MIPS, Doctor?
Like MIPS, okay. How?
2 codes of the same MIPS architecture.
Again, can you repeat this? It's not clear to me.
You write 2 codes by using MIPS.
I'm not talking about your programs. I'm talking about the implementation.
Two versions.
They have the same executing
No, this has nothing to do with the execution time. I'm talking about two different implementations of the same instruction set architecture. How can we have two different implementations of the same instruction set architecture? A simple question. Yani, for example, let us take a look at the Intel architecture. Although I did not really go into the Intel architecture because it's really quite complex. But the Intel architecture defines many instructions. Same thing as the MIPS. So there are many instructions in the Intel architecture. Is it only Intel which is implementing the instruction set architecture? We also have,
there is other.
We have also AMD, right? So AMD has its own implementation, and Intel has another implementation. So when the AMD produces its own processor, these processors are going to implement the instructions. So we have version 1 of the CPU, and we have version 2, and both can execute the same instructions. Okay? So it's really simple, right? For example, the ARM architecture. Okay, the ARM architecture is an example of, it's similar to the MIPS architecture. So ARM has its own instruction set architecture, which is different from the Intel. But you can actually have different implementations. You have two different companies would like to implement the same instruction set architecture, but differently. Okay, so you have two different CPUs are implementing the same instruction set architecture. Even Intel, let us take a look at Intel. Intel, for example, we have, let us say 10 years ago, Intel has produced Intel chips, okay, all generations of the Intel processor. Today, we have new versions of the CPU. They execute the same instruction set architecture. So they implement the same instruction set architecture. They execute exactly the same instructions in binary, but the implementation is different. It has improved. So in the past, and if we go back to 20 years ago, Intel has implemented its own instruction set architecture. Even before that, back in the 1990s, Intel had different implementations of the same instruction set architecture. The same thing for ARM. So they always improve the implementation of the same instruction set architecture. So having like different versions, okay, different CPUs, but each CPU has a better implementation of the previous version, okay, of the CPU. So basically, you have like different implementations over time, and these different implementations will try to improve, okay, the speed of the execution of these instructions. So when I say two different implementations, it means that we have two different CPU implementations. Is this clear?
Yes, clear.
Type. So now here we have machine A. When I say machine A, I mean CPU A or computer system A. It has a clock cycle here of 250 picoseconds. And it has a CPI of 2.0. Now, what does it mean to say 250 picoseconds? What will be the clock frequency? If the clock cycle is 250 picoseconds, what will be the clock frequency?
25 maybe.
I need a number. Yes, Khalid?
4 times 10 to the power 9 hertz.
So 4 what? What's the unit?
4 times 10 to the power 9 hertz, which is gigahertz.
So 4 gigahertz, 250 picoseconds. So if the clock cycle time is 250 picoseconds, then the clock frequency is 4 gigahertz. Okay, so do you see this? You can just quickly convert from the cycle time to the clock frequency. So 250 picoseconds means 4 gigahertz. Okay. How about if the clock cycle is 500 picoseconds? What will be the clock cycle? Sorry, what will be the clock frequency? So the clock cycle is given here, 500 picoseconds. What is the clock frequency?
2 gigahertz.
2 gigahertz.
Yes. So which one has a higher clock frequency? A or B?
A.
Okay. But the CPI of A is 2.0. So on average, it takes 2.0 cycles per instruction. Whereas in the case of B, the average is 1.2. Which is better, CPI, which is 2.0, or CPI, which is 1.2?
It will be B better, or
No, the question is, which machine has a better CPI?
Machine B.
yeah, yes, machine B,
Why?
because it has less cycles.
Yes.
I mean,
So the lower the CPI, the better. That's it. The lower the CPI, the better. Okay. So B has a lower CPI than A, but A has a lower clock cycle. So the clock cycle of A is better than B, but B has a better CPI. So the question is, which machine is faster for this given program, and by how much?
We multiply them together, but we omit the instruction count. The first one would be 500. The second one.
So it says a given program. So we're executing the same program on computer A and computer B. It's exactly the same program, right? So the instruction count is the same. Okay, so basically we're executing the same program. You are taking the same instructions and executing them on CPU A and CPU B. So here both computers are going to execute the same instruction count. So assume that the instruction count is I. We don't know what is the instruction count. It can be billions of instructions. Now, in the case of the CPU execution time, so we have to go back to the CPU execution time. So the CPU execution time on A will be I multiplied by 2.0. That will be the average CPI, multiplied by 250 picoseconds, right? That will be the clock cycle time. So this will give you 500 I picoseconds, because this is execution time, and therefore picosecond is a unit of time, because the clock cycle is given in picoseconds. If you repeat for CPU execution time on B, you get I, the same I, instruction count, multiplied by 1.2, multiplied by 500 picoseconds. This will give you 600 times I picoseconds. By just looking at these numbers, I is the same instruction count, because you are executing exactly the same program, exactly the same instructions. Now, which one do you think is better, A or B?
A better.
Why?
Because it takes less time from B.
So less time means better, right?
Yes.
So clearly here that which machine is faster. So when I say machine, it means that which CPU, okay? So here A is faster than B. That's the first answer. And I should not really show you this. By how much? By how much?
We
Can take the ratio.
Exactly. So when I would like to compare two different CPUs, if I would like to compare the execution time on A versus the execution time on B, the way to compare them is to divide. Okay. So in order to compare, we divide. So we divide here. We said that A is better than B, is faster than B. But in order to find out by how much, we divide the execution time on B, which is 600 I picoseconds, divided by the 500 I picoseconds. So we divide the longer execution time than by the shorter execution time. Now I divided by I will cancel each other, and therefore we get 6/5, which is 1.2. So now we can say that A is faster than B by a factor of 1.2, and 1.2x faster. That's what it means. Okay.
Or we can say 20%.
Yes, 20% faster. Yes.
Doctor, I have a question.
Yes, تفضل عمر.
I'm not sure I understand the first bullet point when you said that the ISA is still the same used by companies, but they improved the performance. Do you mean that they changed other aspects like organization and whatnot, or was there another thing?
Of course, yes. So when I say two implementations, it means that here we have two different CPUs. So when I say two implementations here of the same ISA, So we have two CPUs that have implemented exactly the same instructions.
I see. Okay, thank you.
Okay, and even the same company, for example, every few years it produces a new CPU, and it will tell you that this CPU is better than the older one. Why? Because it has improved the organization, it has improved many things inside the CPU. So therefore, when I say implementation, it means that the way that the instructions are implemented, the organization of the CPU has changed. That's the meaning of the implementation. It will give you a new CPU, okay, which is a different chip, which is different from the older one. And this implementation should be better than the older one. Okay? So
Yes.
here, for example, you can also have two different companies are implementing the same ISA. For example, Intel and then AMD. AMD actually were a group of engineers at Intel, but they actually were excellent engineers, and they left Intel and they decided to make their own company, and they call it AMD. Okay, but they implement exactly the same instruction set, but they want to compete with Intel and show that they can actually have even better CPU. So they are implementing the same ISA, the same instructions, but producing, okay, different chips, different CPUs, okay, that can have a different implementation, okay, and they would like to compete. Okay, so is your CPU better or my CPU better? Okay, that's really the idea, okay? So when I say two implementations, it means that the way that the CPU is organized can be different. The way that the instructions are implemented can be different. So the idea is to compete and to show that I can have a better implementation that can result in a faster execution of the instructions. Okay? That's really the idea.
Yes, thank you. Very clear.
Right, okay. Right, so now, how do we determine this average CPI? So we have seen that you can have different types of instructions. So if you have different types of instructions here, they have different CPI. Okay, we have seen that before. Yeah, for example, if you have addition and multiplication, typically would take longer than addition, right? Division typically would take longer than multiplication and addition. So it depends on the type of instruction. The same thing if you have a floating point instruction, let us say floating point addition, typically it will take more clock cycles than to execute than the simple integer addition. We have seen that, right, in the quiz. When I was looking at your solutions in the quiz number 4, I was surprised that you are putting the exponent with the significand together and adding them. This is not a way to add. Okay, so I will post the solution, okay, on Blackboard. I forgot to post it yesterday, so I will post it so that you can go over the solution. So this is not the way to add, okay, floating point numbers. So you have to compare the exponents. Of course, yeah, many have done it. They had perfect answer, okay, on this quiz. But others did not understand. Yeah, I spent like many lectures talking about floating point, and still most of you did not really get it. And floating point is essential part of any computer system because this is how you represent, let's say, numbers that have a fraction, okay, or real numbers. But there is an exponent. So this is what we use it to represent the scientific notation, which is used many programs that do scientific computation. So this is actually used by scientists and by engineers. So many programs depend on the floating point numbers and the floating point arithmetic. Anyways, coming back here. So when we talk about different types of instructions, they have different CPI. So this CPI means the clock cycles per instruction. And this can change from one instruction to another. So what we can do is that we can define here CPI sub I, which is the number of clock cycles for class I of instructions. Yani, for example, I might have one class for all the ALU instructions. So this is one class. I might have a second class for, let's say, the branch instructions, or for the load instructions, or store instructions, or the floating point, and so on. So we can distinguish between these different classes of instructions based on their CPI. And then I can count in my program I can actually have the count here C sub I. This is the count of instructions for class I of instructions. So I can count, for example, let us say if class 1, if I say C1, C1 will be the count of ALU instructions. C2 might be the count of the load instructions, for example. C3 might be the count of the store instructions. So these might have, okay, different counts inside my program. So just count the instructions. So this is the meaning of C sub I. And therefore, we can determine the total number of CPU cycles by counting C sub I, okay, which is the class I of instructions. So count the instructions that are of class I, and then multiply it by the CPI sub I. So this is how we calculate the number of CPU cycles, and of course add. So this is the meaning of the sigma here notation. So basically, we multiply CPI sub I multiplied by the count C sub I, and then we add across all the classes of instructions. So if I have n classes, so we have to take the sum of all of these terms to get the total number of CPU cycles. Now that's how we count the number of CPU cycles. We can determine the average CPI by dividing the total number of CPU cycles, which is shown here on top, and dividing it by the total instruction count. The total instruction count is the sum of C sub 1 plus C sub 2 plus C sub 3 and so on. So I write it in sigma notation, okay, the sum of C sub I, where I goes from 1 to n. That's the meaning of the sigma notation. It is just actually adding, okay, all of these counts. Now we can obtain this by a detailed simulator. Sometimes we don't really have the hardware, we don't really have the CPU. I would like to simulate the CPU. The CPU has not really been built yet. So I can do a detailed simulation, okay? Look at the given program, count the instructions, count the number of CPU cycles, okay? Or do this sigma, okay? So add the CPI sub I multiplied by C sub I. So use this equation to determine the number of CPU cycles, and then divide, and this will give you the average CPI. You can also do it if you have a real CPU. And in the case of a real CPU, today actually CPUs, if you have a real CPU, they have counters inside the hardware. These counters are used to count the total number of CPU cycles for a given program, and also count the total number of instructions. So you have the total number of instructions, and you have the total number of CPU cycles. So you can actually calculate the average CPI. So using counters, hardware counters, okay, inside a real CPU allows someone to determine the average CPI. So it can be done either way, either using simulation or doing it directly by executing a real program on a real CPU and using counters in the hardware to obtain the total number of clock cycles and the total instruction count, and dividing to calculate the average CPI. Okay, so that's how we can determine the average CPI. Now that's important. Now notice that the average CPI might change from one program to another. And even on the same CPU, without changing the CPU, just the same CPU, if you run different programs on the same CPU, you might actually get different CPI. So the CPI will change from one program to another. It's not the same. And if you take the program and you run it on different implementations, different versions of the CPU, yani for example, let us say Intel will have different generations of the Core i7. Okay, so if you take it actually from one generation to another generation, you will also get a different CPI. Okay, because the implementation, okay, has changed, and the total number of clock cycles will change, and therefore the CPI will change, even for the same program. So when you take it from one CPU to another CPU, you will get a different CPI. Now, for different programs, you will get different CPIs, even on the same CPU. Okay, so that's interesting because there is no fixed CPI. Okay, that can change from one program to another program. Okay, even when you are running these programs on the same CPU. And also it will vary from one implementation of the CPU to another implementation, even if you are executing the same program. Here's an example on determining the average CPI. So here a compiler designer. Now that's interesting because it will tell you about compilers. So here we have a compiler designer, okay, is trying to decide between two code sequences. Okay, two code sequences. So he wants to look at the hardware implementation, okay, and he found that there are only 3 different classes. For simplicity, I'm showing only 3. So only 3 different classes of instructions, only 3. So these are called A, B, and C. So these are the 3 different classes, and they require 1, 2, and 3 cycles per instruction. So in other words, class A, every instruction of class A, for example, A can be, let us say, the ALU instructions. Okay, so every instruction of class A will require 1 cycle. Every instruction of class B will require 2 cycles, and every instruction of class C will require 3 cycles. Okay, that's very simple. Now, the compiler designer can generate for the same program, which is written in high level, he can generate 2 code sequences. So the first code sequence has 5 instructions. Is using 2 instructions of A, very simple program. So only 2 instructions of A, only 5 instructions. 2 instructions of A, 1 instruction of B, and 2 instructions of C. That's the first code sequence. It only has 5 instructions. And the second code sequence has 6 instructions, 4 of A, 1 of B, and 1 of C. Now, what we would like to do is that we would like to calculate the CPU cycles for each sequence. So what is the total number of CPU cycles for sequence, the first sequence? And what is the number of CPU cycles for the second sequence, and which one is faster? Okay, let us address the first question. Yes, Amr, Fadal.
No, nothing. I thought you were asking.
Right. So yeah, I'm asking now. Okay, how do we calculate the CPU cycles for the first sequence and for the second sequence?
We just multiply the CPI with the CPI of the instruction class by the instruction class, by the number of instructions it has.
Yes, so let us do it for the first code sequence.
2 times 10.
So tell me the computation. 2 times
2 times 1
yes.
plus 1 times 2 plus 2 times 3.
Exactly. So that actually is for the first sequence. It's 2 times 1 times 1 times 2 plus 2 times 3. We get 10 cycles. Very simple, right? So the math is really is very simple. Now that's for the first sequence. Let us repeat it for the second sequence. What do you get?
9. 4 times 1.
Yes.
Plus 1 times 2 plus 1 times 3.
Okay. You see, it's very simple, right? So you get actually here 9 cycles. Now, which is faster, the first or the second?
Second.
The second.
Yes. Why?
Because it has less cycles.
Exactly. So less cycles, less time. So therefore, the second sequence is faster. Okay. Even though it executes 1 extra instruction. So notice that the second sequence executes 6 instructions, but it does 6 instructions in 9 cycles. Whereas the first one executes 5 instructions in 10 cycles. Okay. So the second sequence is faster. Why? Based on the count of cycles only. It has nothing to do with the instruction count. It has to do with the number of clock cycles, because cycles means time, right? So this is why we look at the number of clock cycles. Right. What is the CPI for each sequence? Can you tell me what's the CPI for the first sequence? What's the CPI for the first sequence? Somebody can answer?
2.
How did you calculate this?
Number of cycles over total number of instructions.
Okay, so how many instructions we have?
5.
5.
So 10 divided by 5 will give me 2. Okay, for the second one?
9/6.
Yes, which is 1.5.
1.5.
Yeah, yes. you get here the CPI for the first sequence is 10/5, you get 2. And the CPI for the second sequence, you get 1.5. It's 9/6, which is 1.5. So clearly
Actually,
here,
1.8.
yeah, so clearly the CPI for the second sequence is better than the CPI of the first sequence. Now, this shows that the compiler itself can translate sometimes the same code, it's the same high-level program state. This is just, let us say, one statement in your program. It can translate it differently. So there will be different translations for the same high-level statement. So you are writing the program in high level, and there is actually more than one possible translation. So when it's translated according to the first code sequence, we got 10 cycles. And if we translate it according to the second sequence, we got 9 cycles. And you see that the CPI changed according to the translation, which is done. So we did not change the program. We are just changing the translation, which is done by the compiler. So the compiler here can play a role on how the program is translated. If the compiler does actually a lousy job, then this is going to increase the number of clock cycles and the execution time. If the compiler actually does a better translation, then in this case you will get a faster code that will execute in less number of clock cycles and a better CPI. So you see that the CPI depends on the compiler in this example. Okay, so this shows that how the compiler actually can play a role in improving the CPI and the total number of clock cycles. Now I say that 10 cycles, 9 cycles, if you are using really a very fast clock, the difference is only 1 cycle, correct? So the difference is only 1 cycle.
Yes.
But the clock, but the clock cycle really is a fraction of a nanosecond today. So what are you trying to say? The fraction of a nanosecond? Is this important?
You mean the difference?
So when I say the difference here, okay, between sequence 1 and sequence 2 is just 1 cycle, right?
Yes.
So okay, the difference is just 1 cycle. But really, is it really important, Yani, if you save 1 cycle? It all depends. It all depends on this code. If this code exists in nested loops, okay? So if this is a statement that exists in an inner loop, and you have, let us say, multiple nested loops, and you are repeating these loops, let us say, trillions of iterations. So this sequence, when I say here 10 cycles or 9 cycles, if you repeat trillions of iterations, let us say if you are doing it on arrays, on different elements of an array or matrices or whatever, okay, then if you are repeating the same sequence again and again inside a loop for many repetitions, okay, then in this case, if you repeat it many times, then this 10 cycles or this 9 cycles, you have to multiply it by the number of iterations. And the number of iterations is very large, then it's not 10 or 9, it becomes like 10 multiplied by the count of iterations. And if the count is very large, then this becomes a large number of cycles. So it can make a difference, yes. It can make a difference sometimes. So it all depends, of course, on the program, what you are trying to say. But the idea is that the compiler can impact, okay, the total number of cycles for a given, let us say, program, and also it can impact the average CPI. Right, so let us move on here to the next example. Here's a second example on the average CPI. I really need to move fast because I'm really very slow today. So here, okay, we have, let us say, 4 classes. It shows here class 1 is ALU, class 2 is load, we have store, and we have branch. So these are 4 different classes of instructions. It says 50% of my instruction count are ALU, 20% are load, 10% are store, and 20% are branch instructions. Now you might actually ask me, how did you get these numbers? Well, you can actually just take a program and execute the program and count, okay? You can simulate the execution of the program. You can use a simulator to extract, okay, the total instruction. So we have the total instruction count. You can count the ALU instructions. You can count the load, store, and the branch. And you can divide, okay, the count of ALU by the total instruction count, and this will give you the frequency. the percentage of the ALU and the percentage of the load and the store and the branch. Assuming we only have these 4 classes, 4 types of instructions. And notice that the sum here will add to 100%, which is the total instruction count. Now, it's also given here that the CPI for ALU is just 1. The CPI for the load is 5. For store is a 3, and for branch is 2. So the first question is, what is the average CPI? How do we calculate the average CPI in this example?
First, we need to multiply the CPI by the frequency and take the sum.
Yes.
Right.
This is, yeah. So this is a weighted average. Okay. Now someone will say that let us just add 1 plus 5 plus 3 plus 2 and divide by 4. Is this correct?
No, they have different way.
Okay, so it's not just adding these 4 numbers and dividing by 4. This is not how we calculate the average. This is not a simple average. This is a weighted average because the frequencies of these instructions are different. They are not the same frequency. So we have to calculate a weighted average, as you said, Ali. So we have to multiply. So suppose that we have 100 instructions. 50 will be ALU, 20 will be load, 10 will be store, and 20 will be branch. Correct?
Yes.
So what we have to do is that we have to multiply the instruction count by the CPI. So we did multiply 50 multiplied by 1. We add to it 20 multiplied by 5. And then 10 multiplied by 3 and 20 multiplied by 2. And then we add them up and then we divide by 100, assuming we have 100 instructions. Right, so when we multiply 50 by 1 and dividing it by 100 is the same thing as multiplying 0.5 multiplied by 1, correct? So 50% is 0.5. So it does not really matter, okay, how many instructions you have in the program. You can calculate the average CPI by just looking at the frequency and the CPI for the class. So here we multiply the CPI by the frequency. Now, remember that the frequency, when I say 50%, it means 0.5. That's 50%. When I say 20%, 0.2. So multiply, okay, the frequency by the CPI. You get 0.5 here, you get 1.0, 0.3, and 0.4. Okay, what shall I do next?
Sum of these results.
Okay, and divide by 4?
No, you don't divide.
Divide by 4. Okay.
No,
actually, this is a common mistake, by the way. I can see that people actually love to divide by 4 for one reason or another. But anyways, you just have to add them. Okay, just add them. If you add these numbers, you get 2.2. Very simple math. Very simple math. But unfortunately, some of you cannot really get it. So again, it's simple. Okay, assume that we have 100 instructions. Okay, 50 will be ALU, 20 will be load, 10 will be store, and 20 will be branch. So if you multiply the count by the CPI, this will give you the number of clock cycles. And then when you add them up and then divide by 100, it's the same thing as multiplying 0.5 by 1, 0.2 multiplied by 5, and then all the way here to 0.2 multiplied by 2, and then just add them up. This is the same thing as multiplying and dividing by 100. That's the same thing. Okay, so that's the average CPI. Now this is good. Now the second part of the question is, what is the percent of time used by each instruction class? This is now a different question. Let me ask you this question here now. Okay, we know the average CPI for this given program. Okay, now I said this is actually just a program which is running on a RISC processor. Okay, so if I would like to calculate the percent of time, what's the time which is spent by the ALU instructions on the CPU? And the time which is spent by the load and by the store and by the branch, what shall I do?
Take the CPI times the frequency and divide it by the average CPI, I think.
Divided by what?
The average CPI, it will give you how much time it took.
Excellent, Omar, excellent. So what we need to do is we need to divide this number here, which is 0.5, divided by 2.2. So we get here 0.23 point something, let us say. So this is 23%. Here I take 1.0, which is the CPI multiplied by the, the frequency multiplied by the CPI, and then divided by 2.2, which is the average CPI. So we get 0.45 something. So I can round it up to 45%. This is the same thing here, 0.3 divided by 2.2. This will give me 14%, and this will give me 18%. If you add them up, you get 100%. So it means that 23% of the execution time. So even though the ALU are 50% of the instructions, they only consume 23% of the total execution time of the program. So 23% of the total execution time of the program is used by the ALU. 45%. So even though the instruction count, so only the load instructions are only 20% of the total instruction count, they take 45% of the execution time. That's different, okay? And 14% is spent by store and 18% are spent by branch. If you add all of these weights here, okay, I rounded them here, okay, so you get 100%. Okay, is this clear? That's how we calculate the percent of time. Okay, any questions about this? Students, can you get this?
Doctor, can we convert it from percentage to unit of time? To unit of seconds?
So there is a difference. No, this is actually, well, we don't know what is the total execution time for the program. It's not given. You clearly don't understand it. Okay, I'm just talking to myself. Okay, I can see that. You don't understand it. Okay, fine. Let me show you why. Why did we divide by 2.2 here? Can you tell me, Omar? Let me spend actually just one extra minute. I'm running out of time.
It's just part over the total. That's how I thought about it. Yeah.
Let me explain this. Just 1 second. Give me 1 second. Right. So suppose that, okay, the total execution time of the program, we don't know what's the execution time. So I'm going to use here my pen tool. I hope this is my pen tool. No, it's not. It's my highlighter. Okay, so this is my pen tool. Suppose that T is the total execution time of the program. That's T, right? So the question is, what is TALU? That's the time which is spent by the ALU instructions. So TALU, okay, is the instruction count, which is I, multiplied by the, so, no, this is actually is, let me just write it down again here. It's the instruction count of the ALU instructions. So it must be I ALU. Count the ALU instructions multiplied by the CPI for the ALU. So this is CPI for the ALU. Multiplied by what? By the clock cycle time. So I'm going to just write here by this cycle. But what is T? T is equal to what? The total instruction count multiplied by the average CPI multiplied by the clock cycle time. صح? That's performance equation. You agree, students? You agree?
Yes.
Okay, yes.
Yes.
Right. So what I need to calculate here, I need to calculate TALU divided by T. That's the percent of the time which is spent by the ALU instructions. Now, the IALU is 50% of I. So I'm going to write it down here as a ratio. So the IALU is 0.5 times I. Because it says that the frequency is 50%. Clear?
Yes, clear.
Yes.
The CPI of ALU is equal to 1. So multiplied by 1. Multiplied by the clock cycle. That's the TALU. And we have to look at the total execution time. It is I multiplied by the average CPI, which is 2.2, multiplied by the clock cycle. Come on, cycle divided by cycle, I divided by I. So what we get at the end is 0.5 times 1 divided by 2.2. That's what I did here. Okay, so that's it for today. Thank you very much. Okay, that's the answer why. We divided by 2.2. That's how we calculate the percent of the ALU execution time. You can do it exactly the same for load, for store, and for batch. So I'm going to stop recording.